Hey everybody, we're back with chapter 9, almost done. We have one more chapter after this, and it's not even a full chapter. So if you made it this far, congratulations. We're going to talk about solutions, and then we're going to tie in some other concepts from chapter 11 in the next video, and then that's it for the semester. So pat yourself on the back, you're almost there. So if you are interested in the medical field, particularly if you are in the nursing program, dialysis is definitely something that you're going to learn about. We're going to talk about dialysis at some point in the chapter 9 presentation. But essentially, if you have issues to where you can't remove waste from your body, you end up on dialysis. And this has everything to do with solutions and solubility and calculating solution concentration. So it's really a catch-all concept that we're going to come back to. But first we have to talk about what a solution actually is. So a solution is a homogeneous mixture of two or more substances. So remember way back in chapter 3, we talked about homogeneous versus heterogeneous mixtures. We talked about substances and compounds and all these other terms. So you need to kind of reload those back into your brain. Solutions form when there is sufficient attraction between the solute and the solvent molecules, and we'll talk more about that in a little bit. Solutions have two components: the solvent, which is present in a larger amount, and the solute, which is present in a smaller amount. Solutes, on the other hand, they can be liquid, gas, solid, doesn't matter, okay? And they're spread evenly throughout the solution. You mix with solvents so that the solute and the solvent have the same physical state. So if you have a gas that you're bubbling through a liquid, well, now it's trapped in the liquid, right? You can't filter out a solute, but if you evaporate off the liquid, then you can separate whatever it was that's dissolved. Solutes are not visible, so you can't see a little particle of salt, but you can see different colors depending on what's dissolved in the solvent. This is an example of a solution. So you have copper 2 sulfate, which forms a pretty blue color. And as the crystal dissolves, so the crystal of the copper 2 sulfate was put into this graduated cylinder, and you can see the color is very dark at the bottom, very light blue, and it kind of goes to clear towards the top. Over time, the particles of the solute are going to dissolve, move away from the crystal, and once the crystal is fully dissolved, you're going to get that blue color distributed evenly throughout the solvent. This table gives you some examples of solutions. So some that you might not think about. One example would be air, right? So it's a gas and a gas. There's not as much oxygen in the air as there is nitrogen. There's a ton of nitrogen gas in the air. So oxygen gas is a solute. It's a smaller part than the nitrogen gas. Gas in a liquid, one that you can relate to, soda. So that carbonation that makes you, yeah, that is a gas in a liquid. So remember that. And then some examples of solid in a solid, which you may not think of as a solution, but it is. Brass or steel. So if there, sometimes there are fittings on pipes and things like that, or fittings on tools, those might be made of brass or steel. Let's talk about water as a solvent. Water is called, the universal solvent. It's very, very common in nature. Water is a polar molecule, if you remember your chapter 6 stuff. It's got hydrogen bonds, so if you remember, this is water. It's got that bent shape, and it's polar. Lots of molecules form hydrogen bonds with water, so water is very, very, very essential in terms of being a solvent for biological beings like us. Like I said at the beginning, solutions form when the solute and the solvent have interactions, right? And those interactions have to be big enough to overcome the interactions that the solute has with itself and the solvent has with itself. There's a saying that you may have heard in high school chemistry, like dissolves like. When we're talking about like dissolves like, it means if you have something that's polar, it will dissolve something that's polar, for example. If you have something that's nonpolar, you need to dissolve it in something nonpolar. But you cannot have polar and nonpolar. You can't pair those two together. And that's what this table shows here, the possible combinations of solutes and solvents, what solutions will form and what solutions will not form. So we can make solutions with different things. We talked about ionic compounds again in chapter 6. One great example of that is table salt, sodium chloride. Obviously, it is soluble in water. The ocean is kind of a good example, right? When you take that solid salt as a crystal and dissolve it in water, those crystals have to be hydrated. That means that the water comes in and surrounds the crystal. And that's what this image is showing here. So the green and the purple, that's the crystal of NaCl, the salt. The water comes in, and remember it's polar, so the water can interact with the positive and the negative ions, because there's the partial positive, and let me again draw water out here so that you can see what I mean. We've got partial negative up by the oxygen, and the hydrogens are partially positive. So the partial positive can interact with the chloride ion, which is negatively charged. And the oxygen can interact with the sodium ion, which is positively charged. So as that salt breaks up, you break up into sodium ions and chloride ions, which are now interacting with water. They're surrounded by water. With solutions with polar solutes, for example, methanol, which is an alcohol, it's soluble in water because it has a polar OH group. So the way that I like to write methanol is like this. And I know we did that before in a chapter, and y'all were like, is that the same thing? Yes. That is a polar group, this OH here. And it can interact with the water, so it can form hydrogen bonds. Because it can form those hydrogen bonds, it can be dissolved. Now on to nonpolar solutes. Remember, like dissolves like. So water is not going to help us here because water is absolutely a polar molecule. So if you have something like oil, oil and water don't mix, right? You've heard that before. If you're trying to make salad dressing, you've got an acid and oil. They don't really mix. You got to shake it together or something. You got to force them together. Nonpolar solutes. You need something that's nonpolar. So let's do a quick learning check. Identify the solute in each of the following solutions. The trick here is remembering that the solute is present in a smaller amount than the solvent. So we're looking for something that's small relative to the other compound. So we've got 2 grams of sugar and 100 milliliters of water. 2 grams of sugar is definitely going to be smaller here, so that's going to be our solute. 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol. 30 milliliters is smaller, so that means the methyl alcohol has got to be the solute. So that's just to remind you, solute, it's present in a small amount. Now we're going to talk about electrolytes and non-electrolytes. So in the body, electrolytes are really, really important because they maintain what's called homeostasis. That is kind of the normal condition of the cell. And electrolytes regulate a lot of different functions inside of your cells, and they do a lot of regulations with your organs. So sodium, potassium, chloride, all of these things are very, very important. And the levels are very tightly maintained because if they're not, they can do some real damage. Let's first talk about strong electrolytes. They completely dissociate in water. So when we were talking about sodium chloride, table salt, that's an example of a strong electrolyte. It completely dissociates and makes positive and negative ions. In this case, sodium chloride makes sodium ions and chlorine ions, or chloride ions, excuse me. And they form a solution that can actually conduct an electric current strong enough to light a light bulb, okay? Take note of how the dissociation has been written as an equation. We have the solid, we're adding water, which the water is not a reactant, so that's why it's written over the top of the arrow. And then we have the ions. You're going to need to be able to recognize how a strong electrolyte dissociates. So you'll need to recognize it, and you'll need to be able to write it out. Then we have weak electrolytes. So they only partially dissociate. So the solution has some ions, but it's mostly molecules, okay? The molecules have not broken apart. One example of that would be acid. So if you have an acid and water, you're going to make hydrogen ions, and you're going to make some kind of a anion. In this case, we're talking about fluoride ions. Again, we're adding the water, but notice how there's a forward and reverse arrow. That means that the ions can recombine and reform the molecule again. So it's not exactly enough to light a light bulb, but you are going to have some ions in solution. Finally, we get to non-electrolytes. So they dissolve just as a molecule. They don't produce any ions. You can't make any current. And notice, we're just going from one state to aqueous. So a non-electrolyte could be something like sugar, where you have a solid, table sugar, and then you dissolve it in water. Now it's aqueous. That's another example. But methanol, which we talked about, it's polar. You can absolutely dissolve it in water, but you're not making any ions. So take note of how this dissociation looks. This table just has some examples of different electrolytes, strong, weak, and non-electrolytes, and then summarizes what we just talked about in the last few slides, and most importantly, gives you some examples. So you may see these on your homework or on the exam, and it will help you kind of place, okay, if I'm seeing ionic compounds, that means strong electrolyte. If I'm seeing acids, then that's probably a weak electrolyte, that kind of thing. Learning check time. I recommend that you pause it and you give this one a shot. Alright, complete each for strong electrolytes in water. The first one, we have calcium chloride being dissolved in water. Remember, we're going to make ions. We've got calcium, which forms an ion that looks like that, calcium 2+. And the chlorine is Cl-. So that's from chapter 6. Chapter 6 knowledge is going to help you here. So if chapter 6 was a struggle, you need to revisit your ions and then the covalent molecules and things like that to be up to speed on the terminology here. There's a subscript of 2 after the chlorine. So that means that if this molecule breaks up, we're going to have 2 chlorine ions plus the calcium. So the only one that looks like that is C. So don't let those subscripts trick you. Number 2, we've got potassium phosphate. Again, we see a subscript after that potassium. So the potassium ion looks like that. PO4 you need to recognize as phosphate. So don't separate those. That is a polyatomic ion. The only one that looks like that is letter A. Now we're going to write some equations. Write the equation for the formation of a solution for each of the following. We have the partial dissociation of a weak electrolyte, which this is an acid, phosphoric acid. Partial dissociation means that it's not going to come completely apart. So there are 3 hydrogens here. We're only going to be concerned with one of them. Remember, with a weak electrolyte, it's going back and forth, right? So we need the forward and reverse arrow. And since it's only partially dissociated, we're only going to put 1 hydrogen ion and then we need to put the negative ion, which is the conjugate base. We'll talk about that probably in chapter 11. And that's it. For B, we have solid sugar dissolving in water. When you have a solid and it's being dissolved in water, remember to write that water above the arrow. We're not making any ions here because this is not an electrolyte. It's a non-electrolyte. So we just write AQ for aqueous after it. And that's it. We'll do some more practice with these in class. Moving on. We always have to do some math, so I apologize. Chapter 7 and 8, pretty math intensive. 9 and 11 won't be so bad, but there's still a little bit of math. We've got to talk about equivalents of electrolytes. Since we're talking about solutions, we have to talk about concentrations, right? So an equivalent is the amount of an electrolyte or an ion that provides 1 mole of electrical charge, which means either positive or negative, okay? In a solution, the charge of the positive ions is always balanced by the charge of the negative ions. So it's kind of like when we were writing those ionic compound formulas. However much positive charge you have, you got to have the same negative. It's the same thing with solutions. The unit that we use for electrolytes, we're talking about milliequivalents per liter. And that's written like this, MEQ per L. And since that little m is for milli, that means that 1,000 milliequivalents is equal to 1 equivalent. So don't forget those prefixes from chapter 2. It's all coming together, I know. So let's talk about an example. If we have a solution that has 25 milliequivalents of sodium ions and 4 milliequivalents of the potassium ion, it's got a total positive charge of 29, because 25 plus 4 is equal to 29. That's the total positive charge in the solution. We have to balance this out with a negative charge. There's got to be an anion. So if chlorine is in there, you've got the chloride ion, and it's the only one, it has to have a concentration of 29 milliequivalents per liter to balance out all of that positive charge. What's underneath this is a table that gives examples of the ionic charges and the number of equivalents in 1 mole of the substance. So if you have something that's got an ionic charge of 1, it's going to be 1 equivalent per mole. That looks suspiciously like a conversion factor. I know, it is. We're getting there. If you have something that's got an ionic charge of 2 plus, then that's 2 equivalents per mole, and so on and so forth. And it doesn't matter whether or not the ionic charge is positive or negative, it's still the ionic charge in equivalents per mole. So let's do a problem to show how we can use this information. It's a 2-part problem. Laboratory tests for a patient indicate a blood calcium level of 8.8 milliequivalents per liter. How many moles of calcium ion are in 0.5 liters of blood? So we need to go from a volume and concentration all the way to moles of the calcium ion. So let's set that up. First thing we have to do is figure out how many milliequivalents we have in 0.50 liters of blood. We can write that concentration like a conversion factor. I was about to call it a unit factor like we did in Chem 103. They're the same thing. So if I slip up and call it a unit factor, it's the same thing as a conversion factor. So what this will do is give us the number of milliequivalents. But that doesn't really help us yet. Now that we've got that, we need to figure out how many equivalents that is. In one equivalent, there are 1,000 milliequivalents. Because remember, all the way at the end, we're going to be able to convert the number of moles, get the number of moles, from using the number of equivalents per mole of calcium ions. Now the calcium ion we just saw a couple of slides ago, it's calcium 2+. So you will need to remember again from chapter 6 how to figure out ionic charges. In this case, calcium is a group 2 element and it's a metal. So it's going to lose electrons to form that ion, and the group number is going to tell you what its ionic charge is. Since its ionic charge is 2+, that means that we get 2 equivalents of charge for every 1 mole of calcium ions. Remember that charge, the 2, tells us how many equivalents. We can write that as a conversion factor and flip it over as well. So those are the 2 conversion factors that we have to choose from. And since what we're trying to do is go from equivalents to moles, we should use this second one. That will cancel out the equivalents and give us moles of calcium ions. So we've got a lot of numbers here, right? Which ones do we need to care about when it comes to sig figs? The volume has 2 sig figs. So does the concentration. All of these other numbers are exact. So, since we've got 2 sig figs we're dealing with both of these numbers, our answer needs to have 2 sig figs as well. When you do the math, you should get 0.0022 moles of calcium ions. So that's part A. Part B is more of a conceptual question. So if chloride is the only ion that's present, other than the calcium, what is its concentration in millieq per liter? Well, if it's the only one, it has to balance out all of the calcium ions. So it also has to have a concentration of 8.8 millieq per liter. We'll do some more of these in class. Now we're going to connect the electrolytes to health. So all your body fluids have electrolytes in them. And there's a table here that shows electrolytes in blood plasma and selected IV solutions. So hopefully you've never personally had to experience this, but you probably know of someone who's been to the hospital and they've had an IV placed. Not fun, I'll tell you that. The gauge of that needle? No, not of God. But those solutions have ions in them and they're balanced to match your body. Each person has a, slightly different electrolytic composition, if you will, due to what you eat and everything else. So everything varies by patient. But this is just an example, right, of blood plasma levels and then what you might see in an IV solution. So we've talked about electrolytes, we've talked about solutes and solvents, kind of building the foundation of what solutions are and different ways that we can classify them. Now we have to talk about solubility. In this case, what we're looking at is a picture of someone's hand who has gout. So they're very much swollen and it's painful. And what happens with gout is that you have a buildup of waste molecules. So in this case, uric acid, because there's so much of it that it's not soluble anymore in your blood. So that's definitely a very painful problem to have. So solubility is the maximum amount of solute that dissolves in a specific amount of solvent. Solubility is absolutely affected by temperature. It's usually expressed as grams of solute in 100 grams of solvent, and that solvent is usually water. It doesn't mean that you won't encounter solubility for other solvents, or that it won't be in some weird, maybe it's out of 50 grams, solvent. But in general, you'll see grams of solute in 100 grams of solvent. Let's talk about unsaturated versus saturated solutions, because we need to build our vocabulary up. Unsaturated just means that the solution can take more solute. So it's got less than the maximum amount of solvent. So let's say that we had something with the solubility of 40 grams if my concentration, if I've only got 20 grams of solute and 100 grams of solvent, then that means I'm unsaturated. I can add another 20 grams before I hit the solubility of this solute. Saturated solutions, however, they contain the maximum amount of solute that can dissolve, and they have undissolved solute at the bottom. So you'll see some kind of solid on the bottom that represents the stuff that can't be dissolved. The solute that dissolves is crystallizing and then going back into solution, so it's kind of a back and forth type of thing. There's an equilibrium between the solute dissolving and the solute recrystallizing to become a solid. So in our example before, where we had the 40 grams of solute in 100 grams of solvent, and that was our solubility, an example of a saturated solution might be 60 grams of solute in 100 grams of solvent. That would be saturated. So this again just illustrates saturated solutions, where you have unsaturated, you keep adding, and then all of a sudden you start to see buildup on the bottom of the beaker. That's saturated now. So here's a quick learning check to see if you understand the difference between saturated and unsaturated, not just the concept, but putting some numbers to it. So pause it if you can, and then give this one a shot, then tune back in. So at 40 degrees Celsius, which remember, solubility is absolutely affected by temperature, so we have to be specific here. The solubility of potassium bromide is 80 grams per 100 grams of water. So that means anything less than 80 grams of potassium bromide in 100 grams of water is going to be unsaturated. If you have more than that, you're going to be saturated. So identify each of these solutions as either saturated or unsaturated. So if we have 60 grams of potassium bromide added to 100 grams of water, well, we've got 80 grams for every 100 grams, right? That's our solubility. So that means this is absolutely unsaturated. We can add more. 200 grams of potassium bromide added to 200 grams of water at 40 degrees Celsius. That's the same thing as saying 100 grams added to 100 of water. That's absolutely over our solubility. So this is going to be saturated. You'll see some undissolved potassium bromide in the bottom of the beaker in this case. So you'll need to be able to look at problems like this and figure out whether or not the solution is saturated or unsaturated based on the information given. Now, as I said a couple of times, solubility is affected by temperature. In general, solubility will increase as the temperature increases. And that's for solids. So if you're dissolving salt in water, that's always the example. Hot water is going to take much more salt than cold water. However, for gases, it's the opposite. The solubility of gases decreases as the temperature increases. So if you can remember one, which probably the one about solids is the easiest to remember because that's intuitive, remember that the solubility of gases is the opposite. So this is an example. It shows you about the solubility of oxygen gas, carbon monoxide, and nitrogen gas. As that temperature increases, the solubility in water decreases. So here's a learning check. We're going to answer both of them kind of at the same time. So the first question is, why could a bottle of carbonated drink, soda, possibly burst and explode when it's left out in the hot sun? And the second question, why do fish die in water that is too warm? Both of these have to do with the solubility of gases and we just said that the solubility of gases decreases as the temperature increases. My up arrow is for increases. So with the carbonated drink, it's getting heated up while it's sitting out there in the sun. And all that carbon dioxide that's dissolved, it's not dissolved anymore. So it's going to build up pressure because you've got this gas above the liquid because the can is not 100% full of liquid. So eventually it can burst if it gets hot enough and you have enough pressure build up from all the gas. With the fish, we're talking about oxygen being dissolved in the water. So remember, fish don't necessarily breathe, but their gills will take the oxygen from the water so that they can, live. If the water's too warm, then you're not going to have enough oxygen dissolved in the water, and the fish, sadly, will meet their end. So yeah, it's a little bit morbid. Sorry about that. But it's a great case of solubility of gases decreasing as the temperature increases. So if you have fish and you don't like to pay for electricity in the summertime because, it's hot and it's North Carolina, if you're down here, think about the fish. It needs a certain temperature so that you're not taking all the oxygen away from it. So take care of your fish. All right. Now we're going to talk about solubility and pressure. We can't talk about that without Henry's law. So Henry's law says that the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. At a higher pressure, there's more gas molecules dissolved in the liquid. We're back to using our soda example. We've got carbon dioxide dissolved in the soda. Okay, that's the carbonation. Before you open the can, you've got some gas molecules that are hanging out above the liquid. Like I said, that soda can is not 100% full of liquid. There's some air there. There's some space. And in that space, you've got carbon dioxide that is not dissolved in the liquid. And it's a pretty high concentration. Once you open that can, you release the carbon dioxide that was hanging out above the soda. And now you're going to give that carbon dioxide that's dissolved a place to go once it comes out of solution. So notice there's fewer gas molecules after you open the can, and that means that there's fewer in the liquid. So when you have open soda, that's why it goes flat. All the gas is gone. We can't talk about solubility without talking about solubility of ionic compounds. So ionic compounds are only soluble in water when they contain ions that are soluble in water. It makes sense, right? If something's insoluble, then the ionic bonds that are holding the molecule together, whatever compound that is, it's too strong for the water to get in and break it up. The ionic compound is not interested in interacting with the water because it's got some great interactions within itself. And there's a set of rules called the solubility rules that we can use to determine whether an ionic compound would be expected to dissolve in water. So you'll see this table. An ionic compound is soluble in water if it contains one of the following. And we've got this list of positive ions here. So if you see a compound that's got any of these ions, the positive ions, it's soluble. If you see any of these negative ions, the anions, also soluble, but there are some exceptions. So chloride, bromide, iodide, those are all halogens. They're usually soluble, but if you see silver, lead, or mercury 1, it's not soluble. So those are some exceptions. Likewise, sulfate, usually soluble, but if it's combined with barium, lead 2+, calcium, strontium, or mercury 1, then it's going to be insoluble. If you don't see any of these ions in your ionic compound, then it's likely insoluble. So let's do some practice with this. Nope, practice isn't come yet. So this is an example of what it can look like when you're making an insoluble compound. If you mix aqueous solutions and you produce something that something that's insoluble. So you can get some nice colors. This is another example of something that is insoluble, barium sulfate. So barium is one of those exceptions with sulfate. And it's actually used to enhance x-rays. So if you need to see, right now we're looking at digestive tract, right? So it enhances those x-rays. It's a medical use. This table just has some examples of ionic compounds, whether they're soluble in water, and most importantly, the reasoning. Because you're going to have to do that reasoning on your exam. Let's talk through some of these. When we do these examples in class, I'll have the solubility rules there for you. The first one, we have cadmium sulfide. We don't see either one of these mentioned in the solubility rules. So if you don't see cadmium, there's cadmium ions, sulfide ions. Neither one of those is there in that table. So that means if you don't see it in the table, it's likely insoluble. Now we've got sodium sulfate. Anything with sodium, probably going to be soluble. And it's a sulfate, so it's a twofer. Soluble. Lead 2 iodide. Usually the halogens are soluble, but lead 2 is an exception. So it is insoluble. The last one, we have nickel 2 nitrate. Don't see anything on the table about nickel, but nitrates are usually soluble. So we are going to predict that this too is soluble. Like I said, we'll do some more practice in class with the solubility rules. We can use these rules to predict whether a precipitate is going to form, which a precipitate is just another way of saying a solid. But if you mix two solutions of ionic compounds and all of a sudden you have a solid forming, that solid is called a precipitate. So the question is, what precipitate forms when solutions of lead 2 nitrate and potassium sulfate are mixed? So that's just rewriting the question so you can see it kind of in a chemical equation. Not balanced. I'm not going to worry about balancing it here. When we put these solutions together, what it's really saying, because remember, ionic compounds dissolve in water when they're soluble. And if it's aqueous, they're dissolved in water. So we've got ions. So for the lead 2 nitrate, we have lead 2 plus ions and nitrate ions floating around in solution. With the potassium sulfate, we have potassium ions and sulfate ions. When you mix these together, the lead has the opportunity to interact with the sulfate. And the potassium can interact with the nitrate. If that happens, what would you form? Well, we'd form potassium nitrate. And then we have to ask ourselves, is that soluble? Well, anything with potassium, anything with a nitrate is soluble. So that's not going to form a solid, okay? if we put the lead 2 ion together with the sulfate ion, we make lead 2 sulfate. And with our solubility rules, we said, well, sulfates are usually soluble, but lead 2 is an exception. It's insoluble. That means that this is going to be our precipitate. We'll do more practice of these in class, but it's a practice of, one, understanding double replacement reactions, which is what this is, and two, being able to use the solubility rules to determine whether or not you get a reaction, which is forming some kind of a solid. Now we're moving on to concentrations and reactions. We need to be able to talk intelligently about the concentrations of our solutions, and there's lots of different ways that we can talk about concentration. In general, when we're talking about the concentration, you're talking about the amount of solute over the amount of the solution. The amount of the solution, we're talking about solute plus solvent, okay? So don't forget that. The amount of solute you can express in different units, just like the solution. Grams, milliliters, moles, liters, okay? The first type of concentration we're going to talk about is mass percent. So you'll see M/M in parentheses, that's mass by mass, where you have the mass of your solute over the total mass of the solution, which, like I said, that is the mass of the solute plus the mass of the solvent. So if we had a solution like we did that practice, where we had the potassium bromide in water, the mass of the solute, say it was 40 grams, plus the solvent, let's say 100 grams, would be what you put in the denominator. And then you multiply that ratio by 100%. So let's practice. When 42 grams of water is added to 8 grams of KCl, the mass percent concentration is 16%. How do we get there? We have to take the mass of the solute and divide that by the mass of the solution, which in this case, it's the KCl plus the water. And you multiply it by 100%. When you do that, you're putting the 8 grams on top, and then you're doing 8 grams plus 42 grams on the bottom and multiplying by 100%. And that's how you get 16.0. When you're talking about sig figs, you want to worry about this addition first. That's what you should get in the denominator. And now we're doing division and then multiplying by 100%. The 100% is exact. We've got 3 sig figs here. We've got 4 sig figs here. So our answer has to be 3 sig figs. So that's why it's 16.0%. Just wanted to throw that out there because for your homework, you're going to have to deal with sig figs. So let's try a problem. Let's calculate the mass percent. What is the mass percent of sodium hydroxide in a solution prepared by dissolving 30 grams of sodium hydroxide in 120 grams of water? Like we said at the beginning, water is a very common solvent. Generally speaking, you see that, you know that that's the solvent. But as good practice, you should just identify which one is the solute and which one is the solvent. That way, when you're doing your calculation, you won't get it switched. You want to make sure you put the right number in the numerator. So for mass percent, we need the mass of the solute over the mass of the solution, which I abbreviate SOLN, and you multiply that by 100%. Our solute is the sodium hydroxide. The solution is the sum of the mass of the sodium hydroxide plus the water and then you multiply that by 100%. Like I said, for sig figs, you're going to do the math in the bottom first to add those two together. When we're looking at sig figs, we've got 3 sig figs up top. We've got 4 sig figs at the bottom. So our answer needs to have 3 sig figs. When you do the division and multiply by 100%, you should get 20%. Now, there are a couple of other ways that we can do percentages to show concentration. But first, we're going to use this mass by mass to write conversion factors because we're not done with doing math with these. So 8.50%. What that really means is when we're talking about mass by mass, that's the mass percent, 8.50 grams of sodium hydroxide and 100 grams of water. When you write that out, you can write it as a fraction. And that 100 grams is exact. The top number is measured. It's also a conversion factor, so we can write the reciprocal. And my apologies, that shouldn't say water, that should say solution. So those are the two conversion factors that we can write. So remember, 8.5%, we're talking about part out of a whole, and that whole is always 100. So you can write out two conversion factors to use to do more math. Now we're going to talk about some different concentrations. Just like you can have mass percent, you can also have volume percent. Works the same way, only instead of having grams, you have volume. Oftentimes you'll see it in milliliters. So you'll have the volume of your solute over the total volume of your solution. And we'll do some practice with this in class. The other kind of percentage you can have is mass by volume. So you've got the mass of your solute and the volume of your solution. And typically speaking, it'll be in grams per milliliter. Molarity. This is different from the percentages. Like I said, we'll do more work with the percentages in class. It's pretty much once you know one, you know how to do them all. Molarity, however, is a little bit different. Molarity, we're talking about the moles of solute per liter of solution. So the mole is coming back from chapter 7. So if you have a 1 molar solution, which that's what this capital M is, it stands for molar, that means that you have 1 mole of solute in 1 liter of solution. So when you see a concentration like this, you can automatically think of it as a conversion factor. So let's do a little bit of work with the molarity. What is the molarity of 0.500 liters of sodium hydroxide solution if it contains 6 grams of sodium hydroxide? Remember, molarity is moles per liter. We have grams, so we can't just divide 6 by 0.5 and get an answer. Well, we could, but it wouldn't be the right answer. We have to take those grams and convert them to moles first. The way that you take grams and convert to moles, this is chapter 7, we need the molar mass. To calculate the molar mass, you look at your periodic table and you find the mass for sodium, oxygen, and hydrogen. So there is our molar mass for sodium hydroxide. Now we can take those 6 grams and make them a little bit more useful. Remember that the molar mass can also be written as a conversion factor. So that's a little bit of a refresher for chapter 7 if it's a little bit of a struggle bus for you. So now we need to figure out which one we need to use. We need moles, and we need to cancel out the grams. So we're going to have 1 mole on top, and the number of grams in 1 mole in the bottom. The grams cancel. We're left with moles. We've got 3 sig figs here, 4 sig figs here. So we've got to use 3 for our number of moles. We're not done yet. That just tells us the number of moles. We need to divide that by the volume. And that volume has to be in liters. When you do that division, and you account for sig figs, which you should have 3, you get 0.300 molar. If you were just given the number of moles, you could just simply divide. But since we had grams, we had to calculate moles first. So that's the key to this problem. As I alluded to, molarity can be used as a conversion factor. If you have, for example, 3.5 molar HCl, 1 liter of solution has 3.5 moles of HCl. And if you can write an equality, then you can certainly write a conversion factor. So we can use that to do more math, to figure out moles, to figure out how to make a solution of a certain concentration, all kinds of things. This table has conversion factors from different types of concentrations. So we've got percent concentrations like the mass by mass, volume by volume, and then we've also got molarity. So if you struggle with writing conversion factors, these examples are a great place to go to when you need to write out conversion factors and choose one to use in a calculation. Let's do another learning check. Since we just did something where we talked about conversion factors, this problem is probably going to use a conversion factor. Pause it, try it, then check back in. How many grams of sodium hydroxide are needed to prepare 75 grams of 14% mass by mass sodium hydroxide solution? Okay, what does this mean? 75 grams. We need to figure out what that number really is. That's the amount of solution. We're trying to make a solution with that mass, right? And we're trying to figure out how many grams of NaOH. That's the mass of the solute. That's the mystery. What we're given as well is 14% mass by mass solution. That means that we've got 14.0 grams of sodium hydroxide and 100 grams of solution. Now let's write some conversion factors. So the first one we can write has the mass of the solute on top and the mass of the solution on the bottom. The second conversion factor we can write is the reciprocal. We're starting with 75 grams of solution. And we need to figure out how many grams of sodium hydroxide. That means we need to cancel out the grams of solution and be left with grams of sodium hydroxide. So this unit factor, see, I knew I was going to do it. Unit factor, conversion factor, they're the same thing. This conversion factor, the first one is what we're going to use. And again, remember SOLN, that's how I abbreviate solution. Grams of solution cancel, and you're left with grams of sodium hydroxide. When you do the math, don't forget that you're multiplying in your calculator by 75 times 14, then dividing by 100. Don't forget the division, because you will get a very wrong answer. It will be a very big answer, and it will not make sense. So the answer for this one is A, 10.5 grams. as always, we'll do practice in class. Now we're going to talk about chemical reactions. When you have a chemical reaction that involves an aqueous solution, you need a few things to do calculations to determine the moles or the grams of a reactant or product. First thing is you need a balanced chemical equation. And we should remember that from chapter 7, because that's where we can get our mole-mole factors. The molarity and volume of an aqueous solution will help us to figure out the number of moles of whatever is being dissolved in that water. Because when we do calculations, we need to know moles. And we can't just take molarity, we can't just take volume, we need them both. So here's a sample problem. Zinc reacts with hydrogen chloride to produce hydrogen gas and zinc chloride. How many liters of a 1.50 molar hydrogen chloride solution, and this is hydrochloric acid, completely react with 5.32 grams of zinc? Let's figure out what we have here. We've got some zinc. We're combining it with some amount of hydrochloric acid. And we're trying to figure out how much. Don't get confused. This is liters, but we're talking about an aqueous solution. In chapter 7, we were talking about liters in terms of gases. But here, we're talking about liters in terms of the volume of an aqueous solution. What we have to do is go from the grams of zinc to the moles of zinc, and that's using the molar mass. Then we have to go from moles of zinc, to moles of hydrochloric acid, HCl. We need a mole-mole factor for that, and we get that directly from the chemical equation. The last step is to use molarity to get from moles of HCl to liters. Let's get started. Let's fill in some numbers. The molar mass of zinc, you're just going to get that from the periodic table. And I'll color code it so you can match it up. Now we're in moles of zinc. For our mole-mole factor, it's going to be just like before with the B over A. So what we're looking for is the B, and that's the hydrochloric acid. So we look at the number of moles that are present in the chemical equation. There's 2 moles. And then the A is kind of what we want. And this is from your textbook. So that kind of like grams of what you have, grams of what you want. It's using that kind of the diagram there So if you don't remember that terminology, it's okay. So that's our mole-mole factor. Remember that if there is no coefficient in front of something, that means that you assume it's 1. Now we have to use the molarity. Remember that molarity can be written as a conversion factor. So to write out our 2 conversion factors, those are our conversion factors. 1.5 moles on the top, or we can put it on the bottom. The one that's going to help us is the one with moles on the bottom. And I wrote 1 instead of 1.5. My bad, y'all. There, that's better. So we've got 3 sig figs in the number of grams of zinc and 3 sig figs in our molarity. So that's what we're going to go with for our answer. Whenever you have a number in the denominator, like here, remember to divide. You go through and do all that math. You should get 0.108 liters. The grams cancel out with the grams, and you're left with moles of zinc. The moles of zinc cancel, and you're left with moles of hydrochloric acid. Those moles cancel, and you're left with liters, which is what we want. And we'll do more practice of that in class as well. It's very similar to the problems that we were doing in Chapter 7. Here's a concept map for how to do those types of equations. But you're going from whatever you have, grams of A or volume of A, solution volume of A. You use a mole-mole factor, and then you can get to a mass, you can get to a volume using a gas law, or you can get to a volume of a solution using molarity. Again, we'll do practice, so don't worry. Almost done. We'll talk about dilutions of solutions, and then we have one more section, and then you will be done with Chapter 9. So with the dilution, you're usually taking some concentrated solution that you've made, and you're putting a little bit of that with some water together. So you're going to increase the volume and decrease the actual concentration. So if you've ever had, this stuff is nasty to me, but it's cheap. The juice concentrate that's like frozen, you can get like orange juice or apple juice or whatever, the concentrate. You thaw it out, you put that into a pitcher, and then you put in however much water. That's making a dilution. A supposedly delicious dilution. I don't really bang with it though. It tastes kind of bad to me. Okay. So, to formalize what we were just saying, and not talk about my despise for those juice concentrates. With a dilution, you're adding water. So you're increasing the volume of the solution. You're taking a little bit, putting it into a little vial or something, and adding water. The concentration of your solute is going to decrease. But the mass of the solute in solution remains the same. And I'll show you what that really means. So to do calculations with this, we're going to talk about the initial and diluted solutions. If I take 5 grams of salt, right, from the big container, and I put it into a little bowl, it's still 5 grams of salt. It's just separated from its other friends, right? So with a concentrated solution, and you take some out and put it into something else, the number of moles in that volume is going to be the same. We can use an equation, C1V1 equals C2V2, where C is the concentration and V is the volume. The initial conditions, that's going to be the concentrated stuff. It's like our concentrated stock. So think about that, the juice concentrate that's frozen, that's the initial conditions. The diluted stuff is C2V2, and that's after you add water, or whatever you're using to make your dilution, but it's usually water. The concentration can be percent concentration, or it can be a molarity. Doesn't matter here. Likewise, your units for volume, at least for percent concentration, can be milliliters, liters, doesn't matter. With molarity, however, you need to use liters because molarity is moles per liter. So this is just a depiction of adding water to a concentrated solution. When you add water, you just space everything out. So it's the same number of particles, they're just spread out more. Let's try a problem. What is the final concentration when 0.50 liters of 6 molar hydrochloric acid solution is diluted to a final volume of 1 liter? We see the word diluted here, and we're looking for a final concentration. So that clues us in that it's a dilution problem. And we're very likely going to have to use this equation. Let's assign our variables. So the 0.50 liters and the 6 molar, those are the initial conditions. It's saying that that's diluted, so that's where we started. So our initial concentration is 6 molar. Our initial volume is 0.5 liters. The question is asking about the final concentration. So we don't know that, but we know that the units will be molarity. We're told that the final volume is 1 liter. Now that we know what we're solving for, which is C2, just like with the gas laws where I circle what variable I'm looking for, I do the same thing with this equation, just because it's easy to rearrange it improperly. So if you get lost in the math and you need a way to make sure you're solving for the right variable every time, this is a good way to do it, to remind yourself, I'm looking for the concentration, and it's the final concentration. To isolate that, we're going to divide both sides by V2. And you get C1V1 over V2. Let's fill in our numbers. Filling in the right numbers in the right place will also get you tripped up. So writing out these variables, making a little table or chart or something, will help you out there too. It's always best to stay organized. When you do the math and you take into account sig figs, which we've only got 2 sig figs here, you should get 3 molar. Let's do another problem, only this time we've got percent concentration. It's percent mass by volume. What is the percent of a solution prepared by diluting 10 milliliters of 9% sodium hydroxide to 60 milliliters? We need to assign these numbers. We're diluting the 10 milliliters of 9%. So that must be the initial. 260 milliliters, that must be part of the final conditions. Our initial concentration is 9%, and our volume is 10 milliliters. The question is asking what is the percent. So we don't know what that is. That's what we're solving for. And our final volume is going to be 60 milliliters. Again, we're looking for C2. So I'm not going to write out how I do it, because I just did that on the other slide. But make sure that you're solving for the right variable and that you're filling in the correct number for the variable. So our initial concentration is 9%. And our initial volume is 10 milliliters. The final volume is 60 milliliters, and that goes in the bottom. When you do that math, and you take into account sig figs, which you've got 3, you should get 1.50% for that solution. Last section for chapter 9. We're going to talk about the properties of solutions. We're getting into the colder season now, and you're going to be driving still, probably, or on the bus, Uber, something. Be safe. Something that's very important is ethylene glycol. Okay? Put that in your radiator to actually keep it working. So your car has this. If it leaks, that's a bad thing because your car will overheat. So we're going to add some more terminology before we talk about properties. So we've been talking about solutions. At the very beginning, we said that they're transparent. You can see through it. Might have a color, right? Like a pretty blue or something. But you can see through it. It's transparent. Solutions don't separate. Once you mix the salt with the water, that's it. You have to evaporate off the water to get the salt back. Solutions contain small particles, ions, or molecules that you can't filter. So if you pour a solution through a semi-permeable membrane, it's not going to do anything. You're just going to end up with solution and a wet membrane. That's it. Colloids, however, they have medium-sized particles. So the solutions have small particles. Colloids have medium-sized particles. They can't be filtered, but if you use a semi-permeable membrane, you can separate out the particles from the solvent. Here's some examples of colloids that you may not have thought about. Fog, clouds, hairspray. That's a liquid in a gas. So anytime that you have like cooking spray, That's having a gas propellant plus the oil, that you're spraying on the pan. Mayonnaise. It's a liquid in a liquid. That's a colloid, actually. Blood, latex paint. So there are lots of things that you encounter or know about that are actually colloids. So in addition to solutions and colloids, we have suspensions. They're heterogeneous, non-uniform mixtures. So that means that you can look at it and see the difference. They have very big particles that settle out of solution over time. So you can filter these, and you have to stir them to make the particles stay suspended. So if you've ever had a blood sample taken, if that blood sits, the platelets will settle out to the bottom. Muddy water, calamine lotion, if you've ever had chickenpox or poison ivy or poison oak, calamine lotion is a suspension. So this table compares solutions, colloids, and suspensions, puts all those definitions together for you in terms of the types of particles, whether or not the particles will settle to the bottom or not, and whether or not you can separate them, and if so, how. This gives you kind of a visual of solutions, colloids, and suspensions in terms of separating them. So if you have settling, that's going to be at the bottom, right? That's A, where you've got the red squares sinking down to the bottom. That's a suspension. If you can take that solution and filter it, you would get rid of the red squares because suspensions can be filtered just using filter paper. You'd be left with the small particles in the solution and the medium-sized particles in the colloid. If you were to use a semi-permeable membrane, you would be able to isolate both the colloid and the suspension in the membrane, and only the small particles in the solution would be able to freely go back and forth across the membrane. So if you're a visual person, that picture may help. When you add something to water, the properties of that water are going to change. So if you have a solution like we were talking about, or a colloid or whatever, you're going to change the properties. So the vapor pressure changes, the boiling point changes, and the freezing point changes. The vapor pressure above the solution decreases. The boiling point of the solution increases, and the freezing point decreases. These properties depend on the concentration of solute in the solution. When it comes to lowering the vapor pressure, we're talking about having a pure solvent versus solute plus solvent, right? If this picture on the left is the pure solvent, let's say that the solvent is water, you're going to have some water vapor above the liquid. If you add something to it, let's say that you added some salt, you've now got less vapor above the solution. And the reason is you've got particles interacting with the water. So remember that sodium and that chloride are interacting with the water. And it's preventing the water from leaving solution because it would rather hang out with the ions. So you're decreasing the vapor pressure. With the boiling point, it's elevated. So it takes more heat to get that salt water to boil than just pure water. That's why if you're making pasta, get your water boiling first, then add the salt. Won't take as long. Boiling point and vapor pressure are related. So if you've got more solute particles in your solution, you're lowering the vapor pressure. So that means it's going to take more time to build up the vapor pressure to get to a point where that pressure is the equivalent of atmospheric pressure and you get boiling. So you're going to have a higher temperature than the normal boiling point. So again, if we have water with salt in it, it's going to take longer. It's going to take a higher temperature to get that water to boil than just plain water. Your freezing point is going to be depressed or lowered. If you've ever lived in a cold state, like Michigan, well, Michigan doesn't really salt that much, but if you live somewhere where it's cold and they salt the roads because they don't want you to slip and slide on ice, that ice you're not going to form ice because you're putting salt down on the road. So the snow is melting and staying melted for a longer period of time because it can withstand colder temperatures because the freezing point of the water is lower. So instead of 0 degrees Celsius, maybe it freezes at -2 or -5 because you've added some solute. So remember when we talked about solutes and solvents, we also talked about electrolytes and non-electrolytes. The non-electrolytes, like sugar, dissolve as whole molecules, and strong electrolytes dissolve entirely as ions. So with antifreeze, like you put in your car, the ethylene glycol, that's a non-electrolyte. It will dissolve in water, but you're not going to form any ions here. However, if you have a salt, like table salt, that's going to give you ions. So the number of moles of particles in solution, when we're comparing antifreeze versus a strong electrolyte like table salt, you're going to have, if you have 1 mole of antifreeze, that's going to give you 1 mole of particles. Because we're not forming anything, any ions. But if you take 1 mole of sodium chloride and you dissolve that in water, you're making 1 mole of sodium ions and 1 mole of chloride ions for a total of 2 moles of particles in solution. This is important because, again, when we're talking about boiling and freezing, the amount of solute in the solvent affects how much the freezing point will be lowered and how much the boiling point will be elevated. So comparing pure water, which has a freezing point of 0 degrees Celsius and 100 degrees Celsius for a boiling point, if you have 1 mole of particles in solution, the new freezing point is negative 1.86 degrees Celsius. The new boiling point is 100.51 degrees Celsius. This is going to be helpful for us going forward. This is for freezing point. Because you notice a trend. For 2 moles of particles in solution, the new freezing point is negative 3.72 degrees Celsius, which is 1.86 times 2. For boiling point elevation, we've got a difference of about half a degree for every 1 mole of particles. We can use this to figure out the new freezing point or boiling point of a solution. So in the northeastern United States, which I also have lived there, during freezing temperatures, they salt the roads, okay? They use calcium chloride, spread it out on all the main highways, and that helps to melt the ice and keep it melted at colder temperatures. So you're just driving on wet roads versus slick roads. Calculate the freezing point of a solution containing 0.5 moles of calcium chloride in 1 kilogram of water. Remember that 1.86 degrees Celsius for every 1 mole of particles? We're going to need that here. And FP is for freezing point. So we're going to need that conversion factor. And we also need to think about how many moles of particles are in calcium chloride. So if we write out a dissociation equation, we're starting with the solid, we're adding water, and we make calcium ions and chloride ions. The total number of particles, we've got 3 moles of particles here. There's 1 mole of the calcium and 2 moles of the chloride ion. Now we're ready to put together an equation. We're starting with 0.50 moles of calcium chloride in the water. But we don't care about that so much as how many moles of particles. We have 3 moles of particles for every 1 mole of calcium chloride. And for every mole of particles, we're going to have a change in our freezing point of 1.86 degrees. So this is our change in temperature. We can only have 2 sig figs here. This 2.8 degrees Celsius is not the final answer. This tells you how much the freezing point of water has been lowered. So the temperature of the water for the freezing point is going to be the original freezing point, which is 0 degrees Celsius, minus our temperature change. So the new freezing point is negative 2.8 degrees Celsius. We'll do some more examples in class, and we'll also do a boiling point elevation question. But it's the same concept. It's just a matter of whether you're subtracting or adding for that new temperature. When we were talking about solutions and colloids and suspensions, we mentioned something about a semi-permeable membrane. That membrane allows water to flow from a higher concentration to a lower concentration. It also allows very small particles to flow back and forth as well. If we have a solution of sugar, so that's sucrose, on one side, and just pure water on the other, we're going to get a flow back and forth of water across that semi-permeable membrane. If you have solute on one side and not on the other, then you're going to have water flowing across the membrane to where the solute is. And what you're trying to do is kind of equal out the concentration on both sides. That's osmosis. The osmotic pressure is the pressure that would prevent additional water flowing through and being added to the more concentrated solution. As the number of dissolved particles in solution increases, you need a greater osmotic pressure to prevent the flow of water. And that makes sense. If you've got a lot of solute, then you need a lot of water, right? You can do the reverse, which is called reverse osmosis, and there's water filtration systems based on this concept. A pressure that's greater than the osmotic pressure is applied to the solution, and that forces it through the membrane. The flow of water is reversed because we're flowing from low to high water concentration, and you're leaving all the junk you don't want to drink behind, if you're talking about like a water filtration system. So you're leaving all the molecules and the ions in solution, and you're making a really concentrated solution, and then you're purifying the water. So it's used in desalination plants. If you live on the coast, you're familiar with this, because that's how they purify ocean water to put back into, the water that we use, the municipal water. And this process actually requires a lot of energy because we are going against the grain here to remove that salt from the water. We can also think about isotonic solutions and biological systems. So we'll define what isotonic is in a minute. But the idea of a semi-permeable membrane, you can think about a cell membrane. Remember that cells have a cell membrane, or if you're a plant, you might have a cell wall. But that is what keeps all the cell stuff inside. And that membrane has to be very selective about what it lets in and out. That's the same concept as a semi-permeable membrane that you would use in a desalination plant, let's say. Only it's a bit more complex. All of the different solutions in your body, like blood and tissue fluids and stuff like that, they all exert osmotic pressure, okay? And if you're, again, in the hospital and you're having an IV put in, let's say that they need to give you medication or something like that, or you're dehydrated, they need to give you solution that is similar to what your body has. That's called isotonic. So it exerts the same osmotic pressure as body fluids do. So you're not having any kind of change in the electrolytes. What you'll typically see is 5% mass by volume for glucose, 0.90% mass by volume for sodium chloride in an isotonic solution. You will need to remember these numbers because you'll need them. Remember that this is isotonic. And I'll bring that up again. We're going to define it in a minute. So let's talk about tonicness. I just made that word up. It's okay. But you see tonic in these words here. So hypotonic, hypertonic, and isotonic. Iso means same. That means that the solution has the same concentration of solutes or electrolytes as where it's going. So if you've got an IV fluid, it's going to be isotonic to your red blood cells, okay? So your blood and that IV solution is going to have the same amount of salt, same amount of glucose, that kind of thing. Depending on what they're trying to do, that's what it's going to be. So your cells are going to be normal. They're not going to recognize any difference, no changes. If you have a hypotonic, now we're talking about less or fewer. So this solution has a lower concentration of glucose or salt than your blood. When that happens, you're going to have water flowing into your red blood cells to try to balance it out and decrease the concentration in those red blood cells. What's going to happen is they're going to swell, and that's called hemolysis. It's going to swell and eventually burst, and that's really bad. Hypertonic means more. So we've got a higher concentration of your electrolytes or your sugar, non-electrolytes, than in your blood. And what happens there is called crenation. And that's when the water inside of the red blood cell is leaving to try to balance out that higher concentration on the outside. Your blood cells will shrink, which is equally terrible. So remember these concentrations from the previous slide, and then the idea of isotonic, hypotonic, and hypertonic when it comes to red blood cells. So now we're going to go through just everything that I told you. In that slide, I've got individual slides, okay? So hypotonic, we said a lower solute concentration. So water is flowing into the cells, and the cells will burst. Hypertonic, higher solute concentration. Water is going to leave the cells, causing them to shrink. As I said at the very beginning of this video, dialysis, it combines the concept of osmosis, solutions, and all these things that we've been talking about for Chapter 9. With dialysis, you have solvent and small solute particles going through an artificial membrane. That artificial membrane is replacing your kidneys. So if you've had kidney failure or something like that, or your kidney function is greatly reduced, you may need some help in removing those waste particles in your body. And that's what dialysis is for. The large particles are retained inside the machine. So those waste particles like urea are removed from your blood. If that doesn't happen, then you can have issues with gout, and other terrible things. So I think we had a picture of what that looks like. Someone who has gout and really bad gout may actually need dialysis because their kidneys are failing. So you're removing waste products and excess water. You'll need to understand how this works. So your blood is being pumped through this artificial membrane, right? And that's pretty much here. So the coil, it allows certain things out, doesn't let them flow back in. And then what you're left with is cleaner blood. So all the urea and other stuff is going to be left in the tank. And your blood will be purified so you can remove all of those waste products. Let's do a quick learning check and identify whether each of these solutions is going to be isotonic, hypotonic, or hypertonic. Again, you need to remember those concentrations. So, IV solution, or IV fluid, we're talking about 5% mass by volume for glucose, and 0.9% for sodium chloride. So that's what we use in IV fluid. If you're above that, like in number 1, you're at 2%, that means that you're hypertonic. Okay, the concentration of solute is higher. 1% glucose solution, however, is lower. So that's hypo. 0.5% sodium chloride is below 0.9%. So that too is going to be hypotonic. And number 4, 5% glucose solution, well, that's the same. Iso is same, so that's A, isotonic. This is the concept map for Chapter 9. If it helps you to place all the terminology that we had along the way into a nice little graphic, go for it, read it, put it in your notebook. Otherwise, you can skip it. Here are your reminders for the week. So there's no office hours this week. Your Mastering Chemistry is actually combined between Chapter 9 and Chapter 11. We haven't done Chapter 11 yet, but we are starting Chapter 9. So your homework isn't due until the 15th at 11:59 p.m. Eastern Time. But you can get started on the Chapter 9 homework once we go over it in class. You're not going to have any more chapter check-ins. It's the end of the semester. It's struggle time. We're trying to do all the projects and study for all the exams. So don't worry about any chapter check-ins. That's all I have for you. I'll see you in class. Stay safe.